All right, so let's go ahead and apply this. This is case 6. Ideal gas is in a sealed container with a movable top. The chamber has a heating element and allows the temperature to stay constant as the volume expands. Person changes the volume from 125 centimeters cubed to 160 centimeters cubed. If the original pressure was 3 pascals, what is the final pressure? So when we set this up, we can draw this out. We know the volume is expanding from 125 to 160 centimeters cubed. The original pressure is 3 pascals. We want to find the final pressure. So what we're going to need to do is convert our 125 centimeters cubed to meters cubed, right? So what happens with a cubed conversion, if we just had 125 centimeters, and then we would have, 100 centimeters is 1 meter, right? If we want the cubed conversion, right? Cubed conversion, that's centimeters cubed, so this has to be cubed. The 1 is cubed, the meter's cubed, so we cube everything here. So when we end up getting our value for meters cubed, it's going to be very tiny, and that's going to be the volume there. And so when we set this up, we've got our original setup and then our final setup when we convert both of them. So the original volume is 100 or 1.25 times 10 to the negative 4th meters cubed. Our final volume is 1.6 times 10 to the negative 4th meters cubed. And so when we set this up, if we bring this to the other side, right, so PV equal over nRT, the initial state of the gas has to equal the final state of the gas. And it's give and take, right? So pressure and volume, number of moles is N, and then R is the constant, the gas constant, and then T is temperature. So our gas before should equal the gas afterwards. And so if we consider that, we can figure out what's happening with the final pressure. So go ahead and use this, place your values in there. Another thing that we're going to have to pay attention to here, some things can cancel out, right? The number of moles can cancel from both sides. R can cancel from both sides. And so we end up getting a ratio of P, actually both, and R and T, right? Temperature staying the same. So pressure 1 times volume 1 should equal pressure 2 times volume 2. So the initial state of the gas should equal the final state of the gas. It's give and take. And so, yeah, go ahead and complete this one and pause the clip, and when we're ready to check, you can hit play to continue. All right, so we should end up getting a final pressure of 2.34 pascals, and that should make sense because the gas is expanded. Okay, now in this case, what would happen to the volume if temperature was allowed to change but pressure stayed constant? So you can use this gas law simulation again and take a look at this. Again, if you had, temperature is allowed to change, pressure has to stay the same, what would happen to volume? So go ahead and pause the clip, give that a try with FET. Just go to FET, P-H-E-T, and then go to gas properties in the website and give that a try. And then when you're ready to explore this more, you can hit play to continue. Okay, so this is Charles' law. What happens with Charles' law? The volume is linearly proportional to temperature. And this is where the pressure stays constant. So the volume is proportional to temperature. So in other words, as the temperature decreases, right, as we get 200 degrees, 100 degrees, 0 degrees, the volume is getting smaller and smaller and smaller and smaller till theoretically where the volume would be 0, and that would be at 0 Kelvin. And so we know that we're not going to have 0 volume. Some really weird things happen around absolute 0, and in fact they just went below absolute 0 not too long ago. And so that's significant there with, but this should make sense, right? You have the volume is getting smaller and smaller and smaller. The temperature is getting colder and colder and colder. So the volume is getting smaller and smaller and smaller as we go to keep the pressure the same, right? Okay. So temperature being Kelvin, volumes in meters cubed. And we can explore that here with that. With the Kelvin scale, the concept of absolute 0 follows that there, where that's where essentially volume would be 0 and pressure would be 0. We know it's not 0, but that's where that the x-intercept is, right, with a y. And yeah, it starts at 0 Kelvin, and we can use our Celsius scale to compensate with that and evaluate that. So the freezing point in water is 273.15 Kelvin, and then the boiling point is 100 degrees higher. Now in Kelvin, you just say that value in Kelvin, right? It's not degrees Kelvin, so 100 higher than the 273.15. We got that there. All right, so in this one, we'll practice this here. This is case 7. An ideal gas is in a sealed container with movable top. Person changes the volume from 0.0187 meters cubed to 0.00973 meters cubed. If the original temperature was 16 degrees Celsius, what is the final temperature in Kelvin? And the pressures kept same throughout the change. So what I want you to do is go ahead and set this up, gas before, gas after. All right. We'll get this into Kelvin here. So gas before, gas after. See if you can solve for the final temperature in Kelvin. And so once you do that, you can hit play to continue. So go ahead and pause, and then we'll take a look at it. All right. So pressure is the same from both sides. So we can divide both sides by pressure, divide both sides by the number of moles of gas. So that's not changing. And then the gas constant is not changing. So we end up with a ratio of volumes and temperatures. And we should get a temperature of 150.37 Kelvin. So that should be the final temperature. In Kelvin, the initial temperature was 289, okay? And so to keep the same amount of pressure, as this compresses here, the temperature's got to drop to keep the same amount of pressure. Okay, and then in this situation, what would happen if the volume was fixed and temperature and pressure were allowed to change? And so, temperature and pressure allowed to change, but the volume is fixed. So try this in the simulation in PhET under gas properties, and give this a try. See what that looks like if you keep the volume fixed, but then you increase the temperature. What would happen to pressure? All right. So what you can consider with this is, for instance, let's say you had a container like this, a metal container that's a fixed volume, right? And the volume's not changing. So if you keep heating this up and the gases are moving faster and faster and faster inside here, right? Eventually, right, it can be, you can get very, very high pressure. And then if something's wrong where the pressure gets so much, you can have an explosion where one of these valves, if the pressure builds up too much, maybe it'll explode. And so, as you're dealing with higher and higher and higher pressures, it takes more and more and more, integrity of the structure to be able to withstand that. So I show in this clip, an oil tank explosion where, the pressure built up so much that eventually the structure gave way and explodes. So this is the Gay-Lussac's law, where the volume is constant, pressure is directly proportional to temperature, and the pressure is in pascals, temperature